We're now going to talk about some more identities. These ones, however, are going to deal with trigonometric functions where the input to those functions are not just a single variable, but rather an addition or subtraction of variables. These are generally known as the addition and subtraction formulas and will be useful to us as we study the more complex interactions between various trigonometric functions. We're going to start with a certain set of formulas called the cofunction formulas. Within the 6 trigonometric functions, there are some cofunctions. You have sine and then cosine, tangent and then cotangent, secant and then cosecant. And up until now, we've just been using these words without making any reference to why some of them have this co in front of them and why are they paired up in that way. Currently, we haven't seen any reason for tangent and cotangent to be paired up other than they simply are defined using the inverse ratio. And then secant and cosecant aren't reciprocals of one another. Sine and cosine aren't reciprocals of one another. So what's going on? We can see what's happening by sketching out a triangle and noting what happens when we take the function and its cofunction of the two different angles in the triangle. So let's take a triangle like this. I'll go ahead and label the sides A, B, and C. I'll label this angle alpha, this angle beta. And now what I want to do is I want to look at sine of alpha and compare it to cosine of beta. Now sine of alpha is the opposite over the hypotenuse. The opposite side to alpha is C. The hypotenuse is A rather. The hypotenuse is C. Cosine of beta will be the adjacent to beta over the hypotenuse. The adjacent side to beta has length A, and the hypotenuse has length C. In particular, you'll notice that these give the same value. Sine of alpha and cosine of beta give the same thing. Similarly, if I take tangent of alpha, that will be A over B. And if I take cotangent of beta, remember tangent is opposite over adjacent, so cotangent will be adjacent over opposite. And again, we see that they're the same, that tangent of alpha and cotangent of beta are the same. And then finally, we have secant of alpha. That's hypotenuse over adjacent because it's the inverse of cosine. And then cosecant of beta is going to be hypotenuse over opposite because it's the reciprocal of sine. And so we see that, in fact, in each one of these cases, the function of one angle and the cofunction of the other angle are equal to one another. And this is where the cofunction description comes from. It comes from comparing one angle in a right triangle to the other acute angle in the right triangle and saying that, well, sine of alpha is the same as cosine of beta, and so forth and so on. We can express this formula algebraically in the following way. We know that the sum of all angles in a triangle is 180 degrees, which is pi radians, and we want to work with radians here. Now, this means that we know that alpha plus beta plus pi over 2 equals pi. And that's pi over 2 is there because pi over 2 is the radian measure of a right angle. Now, if we solve for beta, we get that beta is equal to pi over 2 minus alpha. So another way we can write down the cofunction formulas is to say that sine of alpha is the same as cosine of pi over 2 minus alpha. And in fact, this is going to be the primary way that we write down the cofunction formulas. So let me go ahead and get a new page and write down the cofunction formulas precisely. So the cofunction formulas are as follows. We have that sine, or let me say here, for any angle theta, sine of theta is the same as cosine of pi over 2 minus theta. Cosine of theta is equal to sine of pi over 2 minus theta. Tangent of theta is cotangent of pi over 2 minus theta. Cotangent of theta is equal to tangent of pi over 2 minus theta. Secant theta is equal to cosecant of pi over 2 minus theta, and cosecant of theta is equal to secant of pi over 2 minus theta. In particular, one of the things that the cofunction formulas allow us to do is to translate between expressions involving a function and its cofunction. If I have any expression that involves sines, I can always replace all those signs with cosines. Now, the reason why we haven't done this a whole lot so far and why we hesitate to do it when trying to prove identities is that the price we pay for switching from cosines to sines or tangents to cotangents is that we have to change the angle inside the function. We change from whatever was in there, theta, to pi over 2 minus theta. So this gives us the cofunction relationships. They're very important, and we're going to use them as we move on to discuss the formulas that tell us how to compute the trigonometric functions of a sum or difference of angles. All right, so let's move on there. So let's look at the addition and subtraction formulas. I'm going to start by giving you the addition and subtraction formulas, and then we'll look at how we can actually apply them, and then look at how we can prove that they are what we say they are. So given any angles alpha and beta, we have the following 6 statements. We have that sine of alpha plus beta is equal to sine of alpha times cosine of beta plus sine of beta times cosine of alpha. So this equation right here says that we can express sine of a sum of angles in terms of the sines and cosines of the original angle. And that's what all of these statements here are going to look like. Sine of alpha minus beta is equal to sine of alpha cosine of beta minus sine of beta cosine of alpha. You'll notice that it has the same sort of form as the previous one, but with a different sign. Now let's look at cosine. Cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha sine of beta. Cosine of alpha minus beta is equal to cosine of alpha cosine of beta plus sine of alpha sine of beta. And then finally, for tangents, we have tangent of alpha plus beta is equal to tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. And then tangent of alpha minus beta is equal to tangent of alpha minus tangent of beta all over 1 plus tangent of alpha tangent of beta. Now, these are complicated formulas. They're more complex than many of the ones that we've seen so far. However, there are a few patterns to them that we can identify to help us to remember it. First of all, it's useful to sort of group together the formulas for sine, the formulas for cosine, and the formulas for tangent, naturally. And then within each group, what you will notice is that the only thing that changes are the operations, are the signs. Things go from plus to minus or minus to plus. So for both of the sine formulas, we have sine alpha, cosine beta, and then sine beta times cosine alpha, and the only difference in the formulas is whether we put an addition in between them or a subtraction. Similarly for cosine, we have the same two terms, cosine alpha, cosine beta, sine alpha, sine beta, and the only difference is whether we subtract or add between them. With tangent, these ones have more terms in them, but again, you'll notice that the locations of the tangent alphas and tangent betas are all in the same spot. The only thing that changes is whether you're adding or subtracting at each point. So this is the set of addition and subtraction formulas that we're going to want to work with. They take some time to memorize, that's true. I recommend spending some time with them, making yourself flashcards or just writing out these formulas many times is a good way of getting them into your mind. A couple things to point out that are slightly counterintuitive, or it's not the very first thing you would expect, but that's helpful for remembering them, is that when working with cosine, the operation that you use in the formula is the opposite of what's going on with the angles inside. So if we're adding two angles inside cosine, that means that we're subtracting the two terms that we get in the formula, whereas with sine, they match up exactly. Also, with the sine formulas, each one of the terms that you get on the right has both a sine and a cosine in it, whereas with the cosine formulas, the two terms are a couple of cosines together or a couple of sines together. So these are the formulas. Let's see how we can use them. Now, the most important way for us to use the addition and subtraction formulas is to determine the exact values of the trigonometric functions at angles that are not one of our standard angles, multiple of 30 or 45. So let's look at an example. Let's find the exact value, that is without using a calculator, of cosine of 15 degrees. So when we run into something like this, what we want to do is see if we can write 15 degrees as a sum or difference of angles that we do know about. So what we might notice is that 15 degrees is equal to 45 degrees minus 30 degrees. And the reason why we like that is that we know about 45 degrees and 30 degrees. We know what the sine of each of those angles are, and so we can work out what cosine of that angle is. So our solution would look something like this. Cosine of 15 degrees is equal to cosine of 45 degrees minus cosine of 30 degrees. Cosine of 45 degrees times cosine of 30 degrees, plus sine of 45 degrees sine of 30 degrees. So using the difference formula for cosine, cosine of 15 degrees is cosine of 45 degrees minus 30 degrees, which is what I meant to write down before, which is, according to the formula on the last page, cosine of 45 degrees times cosine of 30 degrees plus sine of 45 degrees times sine of 30 degrees. And we can work out each of these things. So sketching out a couple of triangles for ourselves. We know that if we've got a 45-degree angle here, that triangle has side lengths, or at least there is a triangle with side lengths 1, 1, square root of 2, with 45 degrees as the interior angle. And then for 30 degrees, we know that triangle, that we have a triangle there with side lengths of 1, 2, and square root of 3. So that means that cosine of 45 degrees is 1 over the square root of 2. Cosine of 30 degrees is the square root of 3 over 2. Sine of 45 degrees is 1 over the square root of 2. And sine of 30 degrees is 1 over 2. So we'll get the square root of 3 over 2 square root of 2 in the first term, plus 1 over 2 square root of 2. And then that simplifies down simply as the square root of 3 plus 1 over 2 times the square root of 2. And there we go. That is cosine of 15 degrees. Now there's not a whole lot of simplification we can do here. There are some other ways of writing this down that you will occasionally see. In fact, if you look in the book, you'll see a slightly different representation of this number, but it's still exactly the same. Now this, of course, this cosine of 15 degrees is not something that we want to memorize. We're not going to sit down and memorize that a triangle with an angle measure of 15 inside a right triangle has side lengths of like square root of 3 plus 1, 2, square root of 2, and then whatever this right-hand side works out to be. But by using the addition and subtraction formulas, we can figure out the cosine of that angle without too much trouble, as long as we can express that angle in terms of other angles that we are familiar with. Let's do another example. Let's find sine of 7 pi over 12. Now 7 pi over 12 we want to try and express as a sum or difference of angles that we're familiar with, because 7 pi over 12 is not one of our standard angles. However, it turns out that we can write 7 pi over 12 as 3 pi over 12 plus 4 pi over 12, which is the same as pi over 3 plus, pi over 4 plus pi over 3. And so, if we want to find sine of 7 pi over 12, that's going to be sine of pi over 4 plus pi over 3. Now, we'll use our formula again. If we have sine of a sum, that's going to give us sine of pi over 4 times cosine of pi over 3 plus sine of pi over 3 times cosine of pi over 4. Make sure that you actually switch which angles you're using and you don't duplicate the same term twice. Well, we can use the same triangles that we did last time, because we know that a 45-degree angle is the same as pi over 4. A 60-degree angle is pi over 3. So from this, we'd get that sine of pi over 4 is 1 over the square root of 2. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. And cosine of pi over 4 is 1 over square root of 2. And so we get 1 plus the square root of 3 over 2 square root of 2, which happens to be the same as we got the previous time, which is really just sort of a happy coincidence. So this is the basic idea behind using the sum and difference formulas to compute the sine, cosine, or tangent of an angle that you can build out of our standard angles by addition and subtraction, but that we don't have memorized right away. All right, so let's talk about how we can prove this. And of all of the 6 trig functions that we looked at, one could try attacking any one of them, except maybe the tangent ones. The tangent ones would be difficult to attack first. But it turns out that a convenient one for us to work with is the difference of the cosine formula. So let's prove that cosine of alpha minus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. And we're going to do that using the unit circle. So I'm going to draw a few random angles. All right, so we'll take the red angle, we'll call that beta. The green angle we'll call alpha. And then we're looking for the difference between them, which I'll do in blue. The difference between them would be the angle alpha minus beta. But of course, we can also draw an angle over here with the same measure. Now what I want to do is I want to look at the points on the unit circle that define the sine and the cosine for each of these angles. So I want to look at this point right here, and this point here, and this one here. So let me label these in the following way. Let me call this point here x1, y1. Let me call the point where the red line intersects x2, y2, and the point where the blue line intersects we'll call x3, y3. Now, what we have is that, for instance, sine of alpha is y1, cosine of alpha is x1, sine of beta is y2, etc. And in particular, we have that sine of alpha minus beta is y3, cosine of alpha minus beta is x3. All right, so we have all that set up. The next thing I want to note is that this distance and this distance have to be the same. We're looking at a couple of triangles here. with side lengths of 1. We're still looking at the unit circle, so all these side lengths are 1. So in particular, the triangle that goes from x3, y3 to the origin to the point 1, 0, the triangle with the blue side, is congruent to the angle with the red and green sides. So the two triangles that we have written here are congruent. So in particular, that means that the distance from x1, y1 to x2, y2 is equal to the distance from 1, 0 to x3, y3. But of course, we can express distances using algebra, using the distance formula. So let's go ahead and see what this says. So the distance from x1, y1 to x2, y2 can be written as x2 minus x1 squared plus y2 minus y1 squared, and then the square root of all that. That's just the distance formula. And that has to equal the square root of x3 minus 1 squared minus y3 minus 0 squared. Now, I'm going to square both sides of this. And I made a typo there. That should be a plus. I'm going to square both sides, and I'm also going to expand both sides. So if we do that, we get x2 squared minus 2x1 x2 plus x1 squared plus y2 squared minus 2 y1 y2 plus y1 squared is equal to x3 squared minus 2x3 plus 1 plus y3 squared. So we've got a whole lot of pieces here. Now, one thing that I want to point out, though, is that we have a whole lot of sums here that are just 1. So x2 and y2, for instance, are the coordinates of a point on the unit circle, which means that x2 squared plus y2 squared equals 1. Similarly, x1 and y1 are the coordinates of a point on the unit circle, which means that if you add them up, you get 1. And similarly, if you take x3 and y3, they're the coordinates of a point on the unit circle, so they sum to 1 also. So if we combine all those together, then on the left-hand side we'll get 2 minus 2x1 x2 minus 2y1 y2, and that equals, well, we've got the 1 from the x3 and y3 squareds, but then we also had the 1 that was just sitting there normally, so we get 2 minus 2x3. So what I can do now is I can subtract 2 from both sides, which will cancel out the 2's, and divide everything by -2. So what that'll get us is x1, x2 minus y1, y2 is equal to x3. But this exactly gives us the formula that we want, because let's go back up to the original formula that we were looking for. The cosine of alpha minus beta is precisely x3, because that's the x-coordinate of the point where the angle alpha minus beta in standard position passes through the unit circle. Now similarly, alpha is the green angle, so cosine of alpha is x1, sine of alpha is y1. Beta is the red angle, so cosine of beta is x2, sine of beta is y2, and this is precisely what we proved. So by using congruence of triangles and the distance formula, we were able to show that cosine of alpha minus beta is equal to the formula that we want. Cosine alpha times cosine beta minus sine alpha times sine beta. All right, so that gives us one of our formulas. Let's talk briefly about how we prove the rest of them. And we won't necessarily go through all of them, but we'll go through a couple to see what the general ideas are. Okay, so we have the difference of cosine of a difference formula, rather. All right, so then let's see, well, what about cosine of alpha plus beta? This one is not too hard to do because we can always write an addition as a subtraction of a negative. So cosine of alpha plus beta is cosine of alpha minus negative beta. And we have the formula for cosine of a difference. So this will be cosine of alpha times cosine of negative beta plus sine of alpha times sine of negative beta. Now, to move on from here, we need to know what cosine and sine of negatives give us. And we talked about this briefly back when we were first talking about sine and cosine. And in particular, we know that for any theta, sine of negative theta is equal to negative sine of theta. Cosine of negative theta is just equal to cosine of theta for any theta. So in particular, this means that cosine of negative beta is just cosine of beta. But then sine of negative beta will be negative sine of beta. So we pick up an extra negative one factor in this second term, which we can bring out to the front and make the operation in between a negative. So this is how we can get the cosine of a sum formula. And it's just using the cosine of a difference formula and the identities that we have for what happens when you take sine or cosine of a negative or of the opposite of an angle. So that takes care of the cosine formulas. Let's look at the sine formulas. And I'm only going to do one of them, leaving the other one as an exercise. So then what if we have sine of alpha plus beta? Well, here's where we use the fact, as we mentioned a little while ago, that we can take any expression involving sine and write it in terms of cosine. We just pick up an extra pi over 2 minus piece to it. We change the angle inside. So this is the same as cosine of pi over 2 minus alpha plus beta. So that's using our cofunction identity. Now we can rearrange this a little bit. Cosine of pi over 2 minus alpha plus beta is cosine of pi over 2 minus alpha minus beta. And in fact, I want to group it up this way as cosine of pi over 2 minus alpha minus beta. Now I can use the difference of cosine of a difference formula, rather, to get that this is cosine of pi over 2 minus alpha times cosine of beta plus sine of pi over 2 minus alpha times sine of beta. But by the cofunction formulas again, cosine of pi over 2 minus alpha is exactly the same as sine of alpha. And sine of pi over 2 minus alpha is the same as cosine of alpha. And that's how we can see that sine of alpha plus beta is sine of alpha cosine beta plus cosine alpha sine beta. All right, I'll leave sine of alpha minus beta to you, but it goes very similarly. You can go through almost exactly the same steps to get there. Let's look at tangent now. Now, a standard thing that we do when we're looking at tangent and trying to work with it is that we express it in terms of sine and cosine, and that's what we can do here. So we know that tangent of, well, anything is equal to sine of that thing over cosine of that thing. Tangent of alpha plus beta is sine of alpha plus beta over cosine of alpha plus beta. And we know what each of these expressions are in terms of just sine and cosine of alpha and beta. Sine of alpha plus beta is sine alpha cosine beta plus sine beta cosine alpha. And then cosine alpha plus beta is cosine alpha times cosine beta minus sine alpha sine beta. And this, frankly, is a perfectly good formula that you could use to describe tangent of alpha plus beta, but sometimes we do want to get things back into talking about tangents. So it's at this point where we want to divide the numerator and denominator by cosine alpha cosine beta. And we want to do that because tangent has cosine as its denominator when you express it in terms of sine and cosine. So when we multiply the numerator and denominator by cosine alpha cosine beta, we get sine alpha cosine beta over cosine alpha cosine beta plus sine beta cosine alpha divided by cosine alpha cosine beta all over cosine alpha cosine beta over cosine alpha cosine beta minus sine alpha sine beta over cosine alpha cosine beta. And now we can start simplifying. We have a lot of cancellation that happens. Cosine betas cancel here, cosine alphas cancel here, cosine alphas and cosine betas cancel here, and a whole lot of things turn into tangents. Sine alpha over cosine alpha is tangent alpha, sine beta over cosine beta is tangent beta, and similarly down below. So we're left with tangent of alpha plus tangent of beta over 1, because everything canceled out in that first term, minus tangent of alpha, tangent of beta. So we can use these formulas in order to determine the sine, cosine, tangent of a sum or difference of angles. Now, if you wanted to find the secant, cosecant, or cotangent of a sum or difference, I recommend just finding the other function, the reciprocal function of that one first, and then just taking the reciprocal. Also, you'll notice that actually deriving these formulas for the sum and differences are a little bit time consuming. These are not the sorts of things you want to do in a timed environment. So you are better off working to memorize these 6 formulas rather than relying on deriving them in a low time scenario. So keep that in mind, and there's enough patterns here that it is possible to memorize these with a little bit of work put into it. All right, so let's see some other types of things that we can do with this sort of structure. So let's let alpha be an angle in quadrant 2 such that cosine of alpha. Oh, sorry, I didn't want to specify. I'm getting ahead of myself as far as the quadrant goes. Let alpha be an angle such that cosine of alpha is negative 3 over 5. Let's let beta be an angle such that sine of beta is equal to 12 over 13. Find secant of alpha plus beta and determine its quadrant. So we have cosine of alpha is negative 3/5, sine of beta is 12/13. We want to add those two and find secant of that. So the first thing to note is that secant of alpha plus beta is equal to 1 over cosine of alpha plus beta. So the first thing that we're going to want to do is to figure out cosine of alpha plus beta, and then once we have that, we'll get to secant, because we don't want to have to memorize sum and difference formulas for secant like we do for the rest of them. Also, I did miss one piece of information that we have here. I don't want to tell you what sine of alpha is, but I want to tell you that sine of alpha is positive. And I do want to tell you that cosine of beta is negative. And then we want to find secant alpha plus beta and determine its quadrant. So we're going to find cosine of alpha plus beta and use that to find secant of alpha plus beta. Let's leave the quadrant for a moment. So we know that cosine of alpha plus beta is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Now, we actually already know some of these values. We know that cosine of alpha is negative 3/5. We know that sine of beta is 12/13. What we don't know are cosine of beta and sine of alpha. So those are what we're going to have to figure out. So we can do that over here. Now, if cosine of alpha is negative 3/5, then that means that alpha lies in either quadrant 2 or quadrant 3. However, we're also told that sine of alpha is positive, which means that we need to be looking at quadrant 2, because sine of alpha is negative in quadrant 3. So our alpha must be somewhere here, where the cosine of negative 3/5 gives us side lengths of negative 3 and 5. Now, using the Pythagorean theorem here, we can see that the other side of this triangle will have length 25 minus the square root of 25 minus 9, which is the square root of 16, which is 4. So that's just by the Pythagorean theorem. So from that, we can work out that sine of alpha is going to be 4 over 5. Now, going on the other side, we have that sine of beta is 12/13, and that means that beta has to be in quadrant 1 or quadrant 4. I'm sorry, quadrant 1 or quadrant 2, sorry. And we are told that cosine of beta is negative. So beta is an angle that also is in this quadrant. In fact, you may, in situations like this, want to just write a totally new diagram here so that you're not getting confused with everything on top of each other. But we have this angle beta, and we have side lengths of 12 and 13. We've got hypotenuse of 13, opposite side of 12. And for this side down here, we get that we've got the square root of 13 squared minus 12 squared, which is the square root of 169 minus 144, which is the square root of 25, which is 5. So the horizontal side of this is 5, but of course that's negative 5 because it's going in the left direction here. So we have that cosine of this angle beta is negative 5 over 13. And so here's where we're going to be able to get our cosine. So multiplying this out, we have, now normally we'd cancel the two 5s in our first term here, but we note that we're not going to be able to cancel anything like that in the second term, so let's just go ahead and keep everything together. So we have negative 3 times negative 5 is positive 15, and 5 times 13 is 65. 4 times 12 is 48. 5 times 13 is 65. So we wind up with 15 over 65 minus 48 over 65, which will give us negative 33 over 65. Now at this point you do want to check and see whether there's any simplification you can do, whether you can reduce this fraction at all. In this case we can't. Now this is cosine of alpha plus beta. It's negative 33 over 65. Therefore, secant of alpha plus beta is equal to the reciprocal of that, negative 65 over 33. Exactly. So that answers the first part of the question. But what about the second part? How do we determine its quadrant? Well, we can use some information that we already have. We have that cosine of this angle, alpha plus beta, is negative 33 over 65. This means that we know that the angle sits somewhere in quadrants 2 or 3, because that's where cosine is negative. In order to determine whether it's in quadrant 2 or in quadrant 3, probably the easiest way to do that is to compute sine of alpha plus beta, and just to see whether it's positive or negative. If it's positive, then that'll tell us that we sit in quadrant 2. If it's negative, that means that we'll sit in quadrant 3. So let me copy the diagrams that we've got here, get a new page as we figure this out. So we have that cosine of alpha plus beta is equal to negative 33 over 65, which is negative, which means that so alpha plus beta is in quadrant 2 or quadrant 3. So let's work out sine of alpha plus beta to figure out which one it is. Sine of alpha plus beta is sine of alpha times cosine beta plus sine of beta times cosine of alpha. And given that we already have all this information, we can just read these off of the diagram. So sine of alpha is 4/5. Cosine of beta is negative 5/13. Sine of beta is 12/13. And then cosine of alpha is negative 3/5. So that gives us negative 20/65 plus negative 36/65, which gives negative 56/65, which is negative. So that means that alpha plus beta is in quadrant 3. And there we go. So we can use these formulas to determine facts about sum of angles, even if we don't know exactly what those angles are, even if we only know things about it like its cosine or its sine. So this is how we can use these formulas for that purpose. Now let's look at one more interesting thing that we can do. This doesn't come up all the time, but sometimes it's useful to be able to express a sum or difference of angles with coefficients in terms of a single one. So let's express 2 sine theta plus 3 cosine theta as an expression involving a single trigonometric function. What we would like to do is manipulate this expression algebraically in order to get it to look something like sine theta cosine alpha plus sine alpha cosine theta, something like that, in order to use the addition formula for sine, for instance. This would be sine of theta plus alpha. That would be just a single trigonometric function. But of course we don't have exactly that. The flexibility comes in that we can sort of use any alpha we want. This formula, the formula for the addition of sine, or sine of a sum, works for any angle alpha. And so if we can be clever about the alpha that we pick, we can make this work. So the way I like to do this is the following. I'll start with the expression that I'm looking at, and I will be a little bit greedy. I'll just put in, this is what I would really like. But everything that I put in, I have to balance. I want to keep an equivalent expression, but one that is closer to what I want. So what I would really love, for instance, is in my first term that I would have a cosine of alpha. Now, of course, I can't just throw in a cosine alpha here. I have to balance that out by dividing by cosine alpha. Basically, what I've done in this step is I've multiplied and divided my first term by cosine of alpha. And I'm going to do the same thing over on the right. I'm going to multiply by a sine alpha, but I'm also going to divide by a sine alpha at the same time. Now, what is alpha? I haven't decided yet. I'm writing down what I would really like to be true, And from there, I'll hopefully be able to figure out what alpha needs to be. Now, from here, I've got parts of this expression that I like, the 2 sine theta cosine alpha and the sine alpha cosine theta, but I've got some parts that don't match up with what I want. We've got the 2 over cosine alpha here and the 3 over sine alpha here. What I want to do now is to find a way to basically take those two terms, those two yellow terms, and factor them out. Now, of course, I'm only allowed to do that if they're equal to each other. So what I want is for 2 over cosine alpha to equal 3 over sine alpha. Rearranging this, if I multiply both sides by sine alpha and divide both sides by 2, I get that I want sine alpha over cosine alpha to equal 3 over 2. Or in other words, tangent of alpha to equal 3 over 2. And as long as that happens, that means that I will be able to factor this expression out, because if tangent of alpha is 3 over 2, then that means that 2 over cosine alpha and 3 over sine alpha are the same thing. So I want to write down how I'm defining my alpha now. So let alpha be such that tangent of alpha is equal to 3 over 2. We know there is such an alpha because, in fact, the range of tangent is all real numbers. You can always find an angle that has a tangent of any number that you want. So if that's the case, then that means that I can factor the yellow terms out. Now, of course, I will just express this yellow term using one of these that I've pulled out. I'll write it as 2 cosine alpha, but remember that's the same as 3 over sine alpha. That gives us sine theta cosine alpha plus sine alpha cosine theta. Now this is really good because now the whole expression right here can turn into just sine alpha, or sine of, rather, theta plus alpha. Now the 2 over cosine alpha we can also work out. So 2 over cosine alpha is the same as 2 times secant of alpha. We don't know exactly what alpha is, but we can write down a triangle to describe it. We know that tangent of alpha has to be 3 over 2, which means that the hypotenuse of this has to be the square root of 3 squared plus 2 squared, or the square root of 13. So that means that cosine of alpha is 2 over the square root of 13. And so 2 over cosine of alpha simplifies down to just being the square root of 13. So we have been able to write down the original expression, 2 sine theta plus 3 cosine theta, as an expression involving just a single trigonometric function. Now, we've got this phase shift, basically, of alpha. Alpha is not a variable here. It's a specific angle. Alpha is the angle such that tangent of alpha is 3/2. Or we could even have said, let alpha be the inverse tangent of 3/2. We could have been very specific like that. But it's a constant. The point is that we express this as a function of a single trigonometric function. Interestingly, one of the things that means is that if you go through this process with any linear combination of sine and cosine like this, you can always write it as just a single sinusoidal function, a single function of just sine or cosine. And in fact, we can read some things off of this immediately. We can see that this, the green function we started with, is a sine function. It's got an amplitude of square root of 13, for instance. It's got a phase shift that we could approximate using a calculator. And so this is a way of expressing a sum of trig functions as a single trig function. This is not something that we do all the time, but it is a useful technique to keep in mind for when we can use this sort of a process.